So, there's not too much more to talk about. Just want to finish this up. Let's add a couple more properties to these lists, okay? The next thing, let's check this out. Let's look back at a picture of the stars. So get off the math stuff. Look at this picture of the stars right here. What's something that's different about these stars, like individual stars on here, that even a little kid could notice? Like if you sent this to a little kid and said, what's something you notice is different about this star and this star and this star and this star? What's something that's very easy to see? Yeah, so they would probably notice the color and the brightness, right? So we've already got the brightness or the luminosity listed. So what we're going to do now is we're going to list the color, okay? So let's talk about color. Is color going to go in the direct list or the indirect list? Can we know the color by looking at it, or do we have to figure out the color from like an equation or something? Is the color going to be direct or indirect? Direct, okay? Color is direct, right? Now, here we go. Let's figure this out. I'm going to write it in a specific kind of weird way. Instead of just writing color, I'm going to write spectrum. And I'll put color in parentheses. Because when we're seeing the color, what we're actually seeing is our eyes combining the spectrum of the object together. Remember, the spectrum is the pattern of wavelengths that a object gives off, and color is how we see those different wavelengths, right? So we can directly measure the spectrum. Now, here we go. This means this next part, we don't have to discuss in nearly as much detail, because we already talked about what we can indirectly find from the spectrum. What's something that we can find about an object by looking at its spectrum? What does the spectrum tell us about that object? This would be stuff we could add to the indirect pile. Yep, somebody said elemental makeup. Let's write that as composition. That's one of them. One of the things we can find is composition. What's something else? What's another important one? So composition's what it's made out of. Good. We got that one. So yeah, you guys are saying movement towards or away. So we can get the velocity towards or away. So let's pop that on here. The speed towards or away. And there's one more. Because remember, on the first test, we learned 3 things. You guys are forgetting it. That's okay. It's the temperature. It's the temperature. Remember, the third thing, by looking at the overall shape of the spectrum, we can learn the temperature of the object. But I'm going to be very careful about how I write that, and I'm going to write it down as surface temperature. And I'm going to put a letter on that one. That's T sub S. Let me get that over there. T sub S for surface temperature. Zoom out a little bit. There we go. The reason I'm saying surface temperature specifically instead of just temperature like we normally do is that in this specific example, remember we learned when we talked about the sun that the part of the sun that you actually see is the surface. And so that means if the spectrum we're getting is technically only telling us the composition and temperature of the surface of the star. We can figure out what the core is doing indirectly from that, but it doesn't come from the spectrum, okay? So here we go. We typically don't need letters for these because they're not going to show up in an equation. So here we go. In general, just to make sure we remember what the temperature tells us, if we look here, If we're looking at these stars, the color, in other words, the spectrum can tell us the temperature. So this red star right here, or this red star right here, what's the temperature of that star like compared on relative to the other stars? What's the red star's temperature like? I don't need a number. I'm just talking, is it medium, hot, or cold for a star? Yeah, it's relatively colder. And as some of you are pointing out, these blue ones are relatively hotter. And then the yellow ones, like our sun, this isn't our sun here, but yellow ones like our sun are medium temperature. So red stars are colder, blue stars are hotter, and yellow stars are kind of medium, okay? And they're all hot for a human being. Like, you die visiting any of them because they're too hot for you. But a red star is not as hot as the other ones, okay? All right, now, check it out. And again, don't worry if you're giving me some wrong answers right now. I do not mind. I do not mind, and I will not remember. It's okay. I just appreciate the effort, okay? Now, there's only a little bit more we need to add to this list, and one other classification to talk about, and then we're done. So let's do this. The last property we're going to add to this list is size, okay? The size of a star. Is that something we're going to be able to directly measure, or something we're going to have to figure out? Size. Is it direct or indirect? Indirect. That is correct. The size of a star is going to have to be incorrect because they're too far away to measure. So when I put this down here, I'm going to put, instead of the word size, I'm going to put the word radius with a capital R. And I'll put the word size next to it. Okay. And the reason I put the word radius instead of the word size is that all stars are ball-shaped. So we can say how big they are by talking about their radius. And if you don't remember what a radius is, if you haven't taken a math class in a while, if this was a star, then the radius would be the distance from the center to the surface. So the bigger the radius, the bigger the star, okay? Now, how do we find the radius? How do we find the radius? With an equation, and this is the final equation here. So let's just write this down. Here we go. L equals 4 pi r squared. This little thing that looks like a whistle. And then the surface temperature to the 4th power. This looks ugly. Don't be scared, okay? I'll make this make sense. Let me zoom in on this. There we go. So L equals 4 pi r squared. This, which is actually the Greek letter sigma, T sub s to the 4th power. Don't leave. I'm going to make it make sense. Let's go through this. What does the L stand for? What does the L stand for right here? Luminosity. Correct. Correct. Luminosity. The R stands for radius. We just said that. And then T sub s stands for surface temperature. 4 pi, that's just a number, so don't worry too much about that. That's okay. And this right here, this is just a constant called the, I'm not even going to write the name out. It's called the Stefan-Boltzmann Constant. You don't need to know the name of it. Don't worry about it. Stefan-Boltzmann Constant. The only thing we need to know is it is a constant. So it's just a number. So it does not change, okay? If we needed to plug numbers into this, we need to know the value of that constant, but we don't need to know it. So what does this particular equation tell us? Let's make this make sense, okay? Here we go. What does it say? It says that the luminosity, radius, and surface temperature are all related to each other, which is not surprising. But we can ignore these constants, the 4 pi and the sigma, because they do not change. So we can kind of look at it just like that, okay? Now check this out. There's no fraction here, okay? There's no bottom. So in this equation, if we were to increase r or t, what would happen to L? If we increase either one of these numbers right here, what would happen to the luminosity? Both of them would cause the luminosity to increase. So essentially, this equation says two things can increase the luminosity. First of all, it says if you make the star hotter, it should be brighter, okay? And that's not a new thing. We learned that on test 1. Higher temperatures mean higher luminosities. Brighter objects are hotter, okay? Hotter objects are brighter, let me put it that way. Hotter objects are brighter, okay? But this also says if you increase the radius, the luminosity will go up. So that means the bigger a star is, the more light it's going to make. And that's also not surprising. Bigger stars have a bigger surface area, so there's more space for light to come out, okay? So what this says is increasing the size or temperature of a star will make it brighter. And that also means that if you want to find the size of a star, you need to know the luminosity and the surface temperature first so you can find the size. So a particular luminosity and surface temperature means a particular size. So again, what I could ask here is this. If you're an astronomer and you want to know what the radius is, what two things do you need to know? And the answer would be luminosity and surface temperature, okay? Now, let me put this together, though. We kind of zoom back out. No! Technical difficulties. Okay, check this out. These will be a couple of hard questions right now. Well, not necessarily all hard. Let's say we have a star that is very small and very cold. Very small and very cold. What's this luminosity going to be like? Is it going to be high or low? If it's very small and very cold, would that be a high or low luminosity? It would be low. It would be low. That is correct. And if you, on the vice versa, if you had a very big star that is also very hot, that would make its luminosity very high. Okay? But here's the tricky question. Here's the tricky question. Let's say you have a star that is very cold, but its luminosity is very high. What must be true about that star to make up for the fact that it's cold? If a cold star is still giving off a ton of light, what must we know about that star to make up for it being cold? It must be very big, okay? Here's another one. What if there is a star that is very small, but it still has a very high luminosity? If there's a star that's very small, but it still has a very high luminosity, what do we know about that star? It must be super hot. So basically, you have to look at all three of these things together: luminosity, size, and temperature.